to 1.7. Modeling with functions. Okay, so here, this is where the rubber meets the road. Okay, this is where all of the word problems that you guys so like and are endeared to come into play, right? Okay, so modeling with functions. So let's look at examples, jump right in. And okay, so if we look at example number one, write the area of a circle as a function of its radius. Okay, so that's pretty simple, right? Example 1A, writing the area of a circle is a function of the radius. Well, the radius, it will be pi r squared, correct? Then for B, they want to write an area with a function as a diameter. So what do you put in the diameter? Diameter is 2 times the radius. So if I took the diameter, I'd have to divide it by 2 to find the radius. Then I would go and put this in. So it's going to be pi over 4 d squared, right? C, now we want to do with the circumference, right? The circumference is 2 pi r, right? So if I take the circumference, if I divide that by 2 pi, that gives me the r. So I would square that, pi r squared, right? So I'm going to get what? Pi c squared 4 pi squared. So this pi and this pi goes away. I have squared over 4 pi. You c squared over 4 pi, right? And that's how we figure this out, okay? In example number 2, we have so in example number 2, we have the square of side, a square of side x inches is cut out of each corner of an 8 by 15 piece of cardboard, and the sides are folded up to form an open-topped box. Okay, so you have 8 by 15. Eight by 15, and you're going to cut out an x by x square here. X by x. X by x squared. So you're going to cut these 4 corners out. You're going to fold the others up to make it a box. Okay, so pay close attention to this one, because this example comes up in this book over and over and over again, okay? So it would behoove you to understand what's going on in this thing, okay? So we have an x by x, 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 x. You're cutting this square out, right? Okay. So to find the volume of the box that you're going to get, you're going to have to find the length and the width and then the height, right? To find the volume, right? So that would be the volume. So the volume is going to be equal to what? So the height is going to be the easiest thing. What's the height of this box? So I'm going to end up with a box that looks like this. So what is this height? What's the height of the box? Lila.
The height of the box?
Yeah, the height of the box right here.
We don't know.
Yeah, we do.
We do?
We do. Because I'm gonna fold this up, right?
Oh, yeah.
So wouldn't it be this guy right here? Wouldn't this be the height?
Oh, like X, yeah.
It's X, right? So it's X. X is the height. That's the easy one, right?
I thought you needed like a number.
So this side, so this is going to be this here, we'll call this L, is going to be the same as this L here, correct? Right? So expression for L would be what? Wouldn't it be 8? You started from 8, and you remove an x from here and an x from here. So it's going to be 8 minus 2x. And then you're going to have the width, right? So the width, Kyle, would be what?
15 or 8.
15 what?
Never mind.
15 minus 2x, right? Again, because you're starting from 15, and you're subtracting this x and this x, correct? You see that? So I started from 15, and I'm taking one x, and I'm taking another x away. So it's 15 minus 2x. So this here is an expression of the volume. Okay? B, find the domain of V as a function of X. In other words, X, what are the restrictions on X here, okay? How much can I cut away at most? In other words, can X be equal to 100? Can I cut away 100 from both sides? Olivia?
No, you can't cut away.
Right? Because I don't have enough, because I have this side as being 8, this being 15, right? So what's the most that I can cut off? Anybody?
4?
4, exactly, right? Because that would be half of 8, right? Right? So 4. So in other words, X has to be this. This is the domain, right? Okay? This is the domain. Okay? And then C, graph V as a function of X. And so that would just be putting this guy here into your calculators. Okay, and if you do that, you can, it's going to come out with that it's just like figure 1.81. So D, how big should the cutout squares be in order to produce the box of a maximum volume? So you would use a trace function and trace to that peak, right? Because if you graph it, you're going to come out with a graph that looks like this, 0 and 4. So we just use a trace function to trace this point and find where the X is right there. Okay, and if you do that, you find that X is about 5/3 inches. Okay, 5/3, 1 2/3 inch. Okay, all right. Again, so even though they don't give you a domain, there is an implied domain here, right? Okay. Okay. So that was kind of fun. Let's see if we can do example number.
I think otherwise.
Huh?
I don't think that was fun.
Oh, you don't think that was fun? This is actually, like I said, this one comes out in the book quite often and also it actually comes out in the calculus book too. Okay. So if you're going to do calculus with me, again, you need to know this. Okay. Example number 3. Protecting an antenna. A small satellite dish is packaged with a cardboard cylinder for protection. The parabolic dish is 24 inches in diameter and 6-inch deep. Find the diameter of a cardboard cylinder. Find the diameter of the cardboard cylinder is, whoa, okay. How tall must the cylinder be to fit in the middle of the dish and be flush with the top of the dish? Okay, so in other words, you have a dish. It looks like this. And inside here, you're going to put a cylindrical looking cardboard here, okay? So if I look at it from a cutaway standpoint, okay, I'm going to have something that looks like this, okay, with a cardboard box inside. This is a cylindrical cardboard thing, cylindrical, because it's going to be a cylindrical around here, okay? So we have the diameter, the parabolic dish has 24 inches in diameter. So this guy here is going to be 12. This guy here is going to be 12. Okay, because it's 24 inches across. And it is 6 inches deep. So from here to here is 6 inches. And the diameter of the cardboard cylinder is 12 inches. The diameter here is 12 inches. So this here is going to be 6. This here is going to be -6. Okay. And what do they want us to find? How tall must the cylinder be? So how tall must the cylinder be? So we're looking at finding this guy here. This H is what we're trying to find. Okay. So how would you find that? So this is a parabola. This is a parabola. So let's find the equation for this function here, right? So we're going to have, it's a parabola, so it's y is equal to kx squared. But I know when x is equal to 12, y is equal to 6, right? 12 and 6, right? So let's go ahead and put that in. So I have 6 is equal to k 12 squared, which means that k is equal to 6 divided by 144. Because 12 squared is 144. I divide both sides by 144. And so I divide this by 6, I get 24. So k is equal to 1. So k is going to be equal to 1 over 24. So this function here is going to be y is equal to 24x squared. Okay, so all I need to do is find, if I can find this guy, right, then I can find this guy, right? So if I'm going to try to find this guy here, so I would find that by putting in x equal to 6. Because when x equals to 6, I can find out what the y is. So y is going to be equal to 6 squared over 24, which is 36 over 24, which is 3 over 2. So this guy here is 3 over 2, 1.5. So the height is going to be 6 minus 1.5. So the height is going to be equal to 4.5. Everybody follow that? So I found out what the y value was when x equals to 6. And that gives me this guy here. When I do that, I get 3 over 2. So this guy here is going to be 6 minus 1.5. So it's going to be 4.5. And okay, that's good, that's good. Functions from verbal descriptions. So, yeah, let's see if we can do those two. Example number 4. Example number 4. Grain is leaking through a hole in a storage bin at a constant rate of 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone is always remains equal to the radius. If the cone is 1 foot tall now, how tall would it be in 1 hour? Okay, so grain is falling down like this, and it's going to form a cone here, which has a radius and it has a height. But the height is always going to be equal to the radius. Okay, so if we call this the radius, that would be r, right? So if I find the volume, what is the volume here? The volume is going to be pi r squared, the base, pi r squared, times the height, which happens to be r here. So I'm just going to call it r cubed, because it's pi r squared times r. So pi r cubed divided by 3, right? Because it's a cone, right? Okay, so this is going to be your volume here, okay? So if the cone was 1 foot tall now, how tall would it be in 1 hour? And it is falling at, or it's draining at 8 cubic inches per minute. 8 cubic inches per minute, which means that in an hour will be 60 minutes, so it'll be 8 times 60. So I have added 480 cubic inches in that 1 hour, right? Okay. So when we first started, it was 1 foot tall, 1 foot tall. So 1 foot tall, which means it's 12 inches, right? 12 inches. So my initial volume, I'll call that V naught, is going to be pi r cubed. So r was 12 cubed over 3. This is the initial volume, right? Then I'm going to add to this much more. For an hour, I guess, so the volume after 1 hour is going to be pi, this guy, whatever this was here. Then you're going to add the 480, right? Add the 480, right? 480, okay? And that is going to be equal to the cone after an hour, and you're trying to find the radius after an hour, right? So it's going to be, this guy here is going to be pi r, I don't know, after 1 hour cubed over 3. So this is what you're trying to solve right here. Okay. So in other words, this is the volume that I started with, 1 foot. This is the volume that I started with. This is the volume that I added after an hour, because for 60 minutes, I added 8 cubic inches per minute. So times 60 would be 480. So this is how much I added. So this is the total volume after an hour, right? And that's going to be equal to this guy. Okay, because this is the radius after an hour. Okay, so let's go ahead and solve for R1. So I'm going to multiply everything by 3. So I'm going to get pi times 12 cubed plus 480 times 3 is equal to pi R1 cubed. Right, let's divide everything by pi. This guy goes away. So R1 is going to be the cube root of that guy. So R1 is equal to the cube root of this pi goes away, 12 this, plus 480 pi times 3. Okay? And if you do the math on that, you get 12.98 inches. Okay? All right, so example number 5. How many rotations does a 15-inch tire make per second on an SUV that is traveling at 70 miles per hour? Okay. So this is one of those favorite questions that people like to ask. The crux of this is to being able to translate the circumference, okay? So we have this guy, and we are going 70 miles per hour, and I want to change this into what? Rotations or revolutions per second, okay? So let's go ahead and change the hour into second first. So I'm going to multiply this by, I'm going to change the hours into seconds. So 1 hour is 360 seconds. So that's simple. Okay, now I have to go from miles to revolutions. So let's go ahead and go 1 mile is 5280 feet, right? I know that. So this guy and this guy cancels out. Now I have, let's go from 1 feet, 12 inches. What was the radius given as? 15 inches, 15 inches, okay. So the feet cancels out, okay. So how many inches are there in a revolution? In a revolution, in other words, if I have a tire that goes like this, if I go from here all the way around, it's one circumference, right? Where the radius was 15 inches, right? So one revolution or rotation is 2 pi r inches, 2 pi times 15 inches, right? So the inches cancel out. What do I have left? I have revolutions per second is where I want to be, right? So I'm done. So it's going to equal to 70 times 5280 times 12, 3600 times 2 pi times 15 revolutions per second. Okay, and if you do the math, you end up with 13.07 revolutions per second. Okay, this is nothing more than a unit analysis. You're just transferring units. Okay, all right. Any questions on what we did so far? All right, if not, we're gonna cut it off right here.